So this is a lecture on Introduction to Sequences. There's no specific homework on this topic, but some of this information is going to help you understand the following topics to come. Okay, so let's get started. So suppose you have a round, flat cake. It's a mathematical cake. It's completely flat, not a real cake, so you can't sneak extra slices by cutting it horizontally. So we have this cake. With one straight cut, I can cut it into two pieces. So let's take a look at what that would look like. So I have a mathematical cake, one straight cut, cuts it into two pieces. Okay. Now, what if I made two straight cuts? I have a mathematical cake here. Two cuts makes 1, 2, 3, 4 pieces of cake. Now, what if I made 3 straight cuts? It's tempting to make my cuts like this. And then I would have 1, 2, 3, 4, 5, 6. But I can actually be more efficient than that. And I'm going to do my 3 cuts to maximize the number of pieces of cake I get, keeping in mind that the pieces don't have to be equally sized. Okay, so I could do 1, 2, 3 straight cuts. And I have 1, 2, 3, 4, 5, 6, 7 pieces of cake. So pause the video and see how many pieces you can get if you make 4 straight cuts or 5 straight cuts. And we're going to make a table of values and see if you can find a pattern. Okay, so let's see what we figured out. We have n will be the number of cuts, and the number of pieces of cake we can get will be p sub n. Okay, so with 1 cut we got 2 pieces. 2 cuts we got 4 pieces. 3 cuts we made 7 pieces. Now if you tried this on your own, hopefully you came up with 4 cuts, 11 pieces, 5 cuts, 16 pieces, and if you were patient and you drew a really big piece of cake, which is important, the more cuts you have to make, you would get 6 cuts, 22 pieces of cake. So this is the number of pieces of cake you can make with certain numbers of cuts. And maybe you see a pattern at this point, maybe you don't. Let's just shelve this for a few minutes and come back to it later. Okay, so a sequence is just a list of numbers. It can be finite, like 2, 7, 20, or it can be infinite, like 2, 4, 6, 8, 10, 12, and on and on and on. The numbers can be random, like in the first example, or have a pattern, like in the second example. So we usually name a sequence with a letter. For example, let's name the sequence 2, 4, 6, 8, 10, 12, etc., 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 the letter A. Okay, so A is going to equal that sequence. So we name the terms of the sequence using the letter A with a subscript. And the subscript tells us where in the sequence to look. So if I ask you what A3 is, you would answer 6, because 6 is the third number in the sequence. So if using the same sequence, 2, 4, 6, 8, 10, 12, what is A5? That would be the 5th number in the sequence. 2, 4, 6, 8, 10. So A5 equals 10. So let's see if we can use our new notation to describe the pattern that's happening in the sequence A. So A2, that's the second number in the sequence, is equal to A1, the first number in the sequence, plus 2. And A3, which is the third number in the sequence, 6, is equal to A2, the second number in the sequence, plus 2. And A4, which is 8, is equal to A3, which is 6, plus 2. And A5, which is 10, is equal to A4, 8, plus 2. So I could say the pattern that's happening here, for any nth term in the sequence, any generic term, is equal to the term before it, plus 2. So the term before the nth, we need to create some notation to mean that. The term before a sub n, we write as a sub what? Well, it should be 1 before n, right? The term before a5 is a4, and the term before a3 is a2. So it needs to be 1 less than n, so we do n minus 1, all in the subscript. So what goes in this little blank right here is a sub n minus 1. We call this a recursive rule. A recursive rule is a rule that uses previous terms of the sequence to calculate the current term. So working with this same sequence, I'm going to try to express the pattern in another way. So A1, the first term of the sequence, which is a 2, is equal to 2 times what? Well, 1. And A2, which is a 4, the second term of the sequence, is equal to 2 times what? 2. And A3, which is 6, is 2 times 3. And A4 is 2 times 4. So it looks like any term of the sequence is equal to 2 times n. A sub 5 would be 2 times 5. So A sub n is 2 times n. We call this an explicit rule. If all you need to calculate the nth term of the sequence is the value of n. You don't need any of the values in the previous terms of the sequence to calculate the current term. So this is not recursive, it is explicit. So, here I've given you a sequence of numbers, 1.5, 3, 4.5, 6. I want you to pause the video for a minute and try to come up with the 5th number in the sequence and S sub 0, the 0th number of the sequence. Okay, so hopefully you've had a few minutes to think about this, and you have seen that the pattern to get from one number in the sequence to the next is to add 1.5. To get from 3 to 4.5, you add 1.5. So to get from 6 to the next number, we should add 1.5, so that would be 7.5. So S5 is 7.5. And to work backwards in the list, we should subtract 1.5. So S0 would be 1.5 minus 1.5, which is 0. So the recursive rule for my sequence, S sub n, is that I need to take the previous number in the sequence and add 1.5. So sometimes it helps to just write this down in English before you try to use the mathematical notation. The previous number in the sequence plus 1.5. And then we say, okay, well, the notation for the previous number in the sequence, the number before the nth, would be S sub n minus 1 plus 1.5. So that's my recursive equation, or my recursive rule, because we use the previous number in the sequence. To write an explicit rule, we say that S sub n is equal to n times 1.5. So this sequence that we just looked at, it's a special kind of sequence. A sequence where the rule to get from one term to the next is to add or subtract a constant is called an arithmetic sequence. So that constant that we're adding here was 1.5. So here's another sequence, G. I want you to take a few minutes, pause the video, see if you can come up with G5 and G0. Okay, so hopefully you see that the pattern in the sequence, G, is that the values are doubling. To get from 5 to 10, we do times 2. To get from 10 to 20, times 2. 20 to 40, times 2. So to get from 40 to the next term, I'm going to multiply times 2, and I would get 80. And then to go backwards to find G0, from G1, I should divide by 2. If going forwards, multiply by 2. To go backwards, we'll divide by 2. So G0 is 2.5. So my recursive rule for G sub n is that G sub n is the previous term in the sequence, which we write G sub n minus 1 times 2. And the explicit rule is a little more complicated, but if we just think about what we're doing here, to get from one term to the next, we're multiplying by 2. So to get to any specific term, I'm going to start with 2.5 and multiply by 2 over and over again. And how many times should I multiply by 2 to get to G sub n? Well, n times. Right? To get to G sub 1, I started with 2.5 and multiplied by 2 once. To get G sub 2, I started with 2.5 and doubled it twice. And to get to G sub 3, I started with 2.5 and doubled it 3 times to get 20. So repeated multiplication by 2 we represent with an exponent 2 to the n. So G sub n is going to be 2.5 times 2 to the n. And G also has a special name. This is a special kind of sequence. When the rule to get from one term to the next is to multiply or divide by a constant, we call that a geometric sequence. So if we go back to the cake cutting problem, we want to try to write either a recursive or an explicit formula for the number of pieces of cake you can get using n straight cuts. So take a couple of minutes, now that you know a little bit more about sequences, and see if you can see a pattern here, and write it out using our new notation for sequences. Okay, so maybe you noticed that the number of pieces of cake is equal to the previous number of pieces plus what turn it is, what number of cuts we're making. So 2 plus 2 makes 4, and 4 plus 3 makes 7. And 7 plus 4 makes 11, and 11 plus 5 makes 16, and on and on. So I want to come up with some way to express this using our new notation. So P sub n, the number of pieces of cake we can get with n cuts, is equal to the previous number of cuts we got, so that would be P sub n minus 1, that's this 2, or this 4, or this 7. We calculate, those are going to be my Pn minus 1s. And then the number we add to it are these numbers, 2, or 3, or 4, or 5. And those numbers are values of n. So a recursive rule would be Pn minus 1 plus n. And an explicit one is possible. It's a little bit more complicated, but we can just stick with the recursive for now. So these are the things you should be able to do after this lecture. And this is a worksheet that is not mandatory, but I am including it for your practice. It has the answers, and you can go through this and work on it for a little bit of extra practice on sequences.